Okay, so we have an exclusive description of work there last time. So this is our description of work. So force times distance is our very basic definition of work. No? Now, when an object is being pulled by a certain angle, then we use a component here. So if we are pulling the body here instead of horizontally, if we pull it at a certain angle with respect to the horizontal line, then what we will be using is Fx, not F that is forming an angle. However, we get Fx by simply using our F cosine theta equation to be able to find that. So that's the one that causes the horizontal motion. So that's the one that we apply here. Now, for objects that are being lifted up, so we also find the work there by maybe applying our work in overcoming gravity. Now, but our unit of work is may have two units. One is erg, and erg is a kind of a very, very small amount of work. Because its unit of force is dynes and the distance is in centimeters. And you'll notice centimeter is a very, very short distance. And therefore, now we see that erg could be a very, very small value. Now, another unit that we use for work is joule. And joule is equivalent to Newton and a distance of meters. So Newton meter, when you multiply the force and the distance in meters, you'll end up with a unit called joule. I think in the English system, it's called as a foot-pound, the unit there. So foot-pound is to what we term as a unit of work or energy in the English system. Now again, the CGS and the MKS may roughly be part of our SI unit. So as an application, we have this one last time, so you can go over that one. Now, in overcoming gravity, we also have this. So weight is determined. So weight is equivalent to the force that is acting vertically. If you overcome that vertical force, which is the weight, and move it vertically as well by providing it with some height, then the product of the force, which is the weight, times the height, gives us the work done in overcoming gravity. So weight times height is equals to work. Work that is done vertically. So that's the work that you do on this yellow object if you move it upwards. So that's equals to mg, which is weight times height. So the unit still now will be in joule. Okay, so just like that one, when you drop this object, so there's a weight of this object, and if you multiply it by how far it falls, then you can have here the work that is done vertically. Here are related examples there which you can study. Now, for our energy equation or energy concept, we realized last time that energy is a thing that we need in order for us to do work. So the capacity to do work is described as energy. Without energy, again, we cannot perform any work on something. So again, just like a particular instrument or tool or machine, we have what we call an input work, or we provide it with some kind of energy. Now, once there is an input energy to a machine, then the machine will now do some output work. So, but without that input, the machine will never do anything. So we have machines like an inclined plane. We have machines like the pulley. So these are called simple machines. Now, these machines will never do anything at all unless you give it first energy. So we call the energy that you give to it or the work that you do on the machine as an input work. Now, once there's an input work on the machine, then the machine will now start to to function, no, which we call as an output. Now imagine a jack, no, we use a jack to lift a car when it is flat. Now that jack again, no, for you to use it, no, you have to provide it first, no, with some input work. No? You have to move some handle there, no, to be able for the jack to turn or for the jack to move up. And when you position it at the right location in your car, then the car will now we will now lift up, no, and you're able to remove, no, a part there like a tire once you, no, again provide first, no, an energy to the jack. So a jack or a jack screw is part of a simple machine, no? And again, screws are examples of simple machines, no, that are used to lift things or to fasten things together, no? So again, the usefulness of machines, no, depends on the energy that we give it first, no? So there are two types again, no? We have potential and we have our, no, kinetic energy, no? So the potential energy relies much, no, on the height, no, that you lift it up, no? So without the height, that object will never have no potential energy, no? So the greater the height that you give it, then the bigger is the potential energy, no? So another factor that affects potential energy is mg, or this is equals to our weight, no? So basically this is weight times height, no? Similar to the equation that we have, no, in overcoming work, no, in overcoming gravity, no? So again, potential, no, is something that is lifting an object to a certain height, no? So the bigger the location, or the higher the location that you position it, the greater is the potential energy in joules. Now, if we are using Newton and meter now as distance. Here are examples that you can study also. No? So you can review this one, no? Where PE again is mg times h. No? Now, for this number two equation, no, we see that when this box reaches the highest, no, point, no, which we do not know, no, which we call as h. Now, what we know here is this length, no, of this slanting part of the inclined plane. No? So this slanted portion is 4 meters long, and the inclination there is around 30 degrees. No? Now, if you have a length of an inclined plane here, no, and an angle, then therefore this opposite side h can be determined. No? Now we realize that to find, no, potential energy, we need height and we need the weight of the object. No? So how much is the weight of this box? Then it may be, no, equivalent to m times g. No? And when we multiply it with the vertical height here, which is the opposite of this inclined plane, then we are able to find now potential energy. No? So that's how simple is the equation actually. No? But first, you have to understand how to find h. And h, no, again, if that's the opposite side, then usually we use the sine function. No? Sine is equal to opposite over hypotenuse. No? So that's equals to sine 30 degrees is equals to h over L. But if L is known, then we will be solving for h, and h will simply be equal to the product of length times the sine of the angle. And therefore, we can solve h here. Now, pairing it now, once we know h and pairing it with the weight of the object, we are now able to find the potential energy of this box, once you place it already at the top, at the highest portion there of the inclined plane. Now, again, inclined planes are very, very useful instruments, or devices. We call it by several names, a stair, a ramp. So a ramp, when people will try to place an object on the second level, and there's a ramp, then it's easier for them to transport it. Now we see that in many supermarkets, in some supermarkets, like I think in the Iloilo Society commercial supermarket, we see that when they transport or when they assist the things that their clients buy. No? They can deliver the goods not to the nearest uh, area, no, where they will take a ride. No, the passengers or the clients will take a ride. So some of the employees, no, inside the supermarket assist, no, in bringing those things by using some kind of a cart, no, that travels along this inclined planes. No? So again, it's easier to transport or transfer things when it is located in an elevated location, no? And you are pushing it up and down, no? The inclined plane. No? Okay, so again, no, we transport things, no? By using this. Even in our buildings, no? There are places there where there's a ramp, no? And it is really, no, required of every building to have, no, a way, no, for disabled individuals or persons with disabilities, no, to be able to get into the building, no, by if they are, especially if they are if they are moving, no, by using a wheelchair. No? So we have that, no, in CPU, no, where our buildings have this ramps, no, where you can push or let, no, a disabled person get into the building. No? So usefulness of an inclined plane. No? Now, another type of energy that we know is the kinetic energy, no, which we derive, no, its equation by using the second law of Newton and then relating it, no, to some equation MA, no, ang atong Newton's second law, no, and again, no, we derive the value of our equation, no, kinetic energy, to deriving it, no, by using the work equation. No? So if F here, no, if the equation for our work is F times S, no, which is force times distance, and F, no, happens to be mass times acceleration, basing on our, no, second law. No? Now, if you substitute that value MA, no, to our F, then that will now be MA times S. No? Now, so what we will see here, that if we will group together acceleration and distance, we will have AS. No? And AS, no, is very related to our equation before, no, in our kinematics, I mean. No? So we were able to derive last time about an equation which is 2AS. And 2AS is equals to BF square minus BI square. No? So BF and BI are our initial velocities and final velocities. No? Now the square of their difference is actually equals to twice, no, the accelerations times S. No? Now if we will simply be needing, no, AS, then we can probably divide 2 on both sides of the equation. No? So AS actually can be equivalent to BF square minus BI square divided by 2. No? So if that's the value of AS, we can replace it back. No? Ang BF square minus BI square over 2, no, to this equation AS and multiply it to M. No? So therefore, the work now, no, if we will use our equation MAS here, can be transformed into M times B sub F square minus BI square divided by 2. No? And this is now the work that we do, no, in changing the velocity of the object. No? Now, when we put or change the velocity of the object, what we are actually, no, adding to the object is kinetic energy. No? So this value BF square, no, over 2, ma-BF square na lang siya once the initial velocity happens to be, no, 0, especially when the object started from rest. No? So we can actually eliminate B sub I, no? That is if, no, the conditions allow it. No? But if there's an initial velocity, then you have to include it in our expression. And therefore, no, the kinetic energy is equals to mvf squared divided by 2. No? So that's how we understand kinetic energy. No? So this is the work that we do, no, in changing the motion or the speed of the body. No? So kinetic energy. No? Now we have also some related expressions here, no, or problems, no, on our kinetic energy. No? Now, for our potential energy, no, and kinetic energy, no, transformation, how does kinetic and potential energy is changed? No? Now, maybe now we can think of an object starting from the ground, no, and we will try to throw it upward. No? And probably to do that, we will need initially an initial velocity. So maybe as this one goes up, you need to provide it with kinetic energy. No? So it will have a kinetic energy right at the very beginning. So we will need here kinetic energy. So there's kinetic energy that is required so that this object can be moved upward. Without the kinetic energy, that object, this object will never go up unless you give it some velocity. So changing the velocity of that object will give you or will require you to give it kinetic energy. So that one will now go up once there is kinetic energy. But you'll realize that as it reaches the highest point, it will stop. It will not go up forever. So it will eventually come to a halt. And once it stays there for a very, very short period of time before it goes down, what it attains, since there's already a height there, that it now has potential energy because it reaches the highest point. So now it stops because there is now a height here. So your kinetic energy was changed into potential for the time being. Now, since there's no more motion at the top, then the kinetic energy at the top will become zero. Now here at the bottom, at the very beginning, since there's no height involved, since it is at the ground level, so supposing this is our ground level, so this is the ground here. Kamahin natin yung ground. So since that's the ground level, there's no height. So the kinetic energy is maybe the greatest here at the bottom, but its potential energy at the bottom will be zero. There would be no potential energy there because the object is not moving or it does not have a height at the bottom. So our kinetic energy at the ground level, so we may have it in symbols KE. KE here is maximum at the bottom, at the ground, because it will be moving at the fastest value. But the PE value is minimum or maybe zero for that matter because there's no height at the ground level. But at the top, you will realize here that the kinetic energy will become zero. Kinetic energy at the top will become zero. There's no motion there. So the kinetic energy will be the least in value. However, since it attains the highest height, then it will have the maximum potential energy at the top. So this is what we say that there is transformation of energy from kinetic to potential as you move it up. Okay, so again, there's no energy here that is actually being created. But all that happens is that energy was simply changed from one form to the next. Now we can call the kinetic and potential energy maybe at the top because this is the end location as KE2 and PE2 ang sa babaw. We can call it as KE2 kaya mo na ng end value and may ara kita ding PE2 man sa babaw or maybe you can call it final F or sa dalom we could have here KE initial muna yung aton nga initial kinetic energy and our initial potential energy. We can call it with a subscript I. Now you will realize that if we add this value together, if you will get a total value there of the energy at the bottom, and if we add up the energy also at the top, you will see that there's sum, no? The sum of the energies at the top and at the bottom, it's always the same. No? It will always be a constant value, or actually, no, anywhere, no, in our location here. No? So every level, the kinetic and the potential energy when added together, no, will always be equals to its final and initial state. No? So ang atong nga total, no, if you try to add this up, no, this will be at a certain constant k. No? So this will be equals to a constant, no? Especially if you have a system that is confined, no? A very, very ideal system. No? So this is what we call conservation of energy. No? The energy at the top, when you add all the energies involved, and including the energies involved at the bottom, they will always be equal to each other. No? So that's what we mean by conservation of energy. So we have a statement for the law of the conservation of energy. No? That energy is neither created nor destroyed, no? But it can only be transformed from one form to another. No? So this is an illustration of that one. No? So here is our illustration, no, for the transformation of energy. So lifting the object again, no, gives the object potential energy. No? But once it goes down now, no, that potential at the top will now change the velocity of the object. No? And the highest velocity will be attained, of course, no, when it is about to reach the ground. No? So since that will be the maximum velocity, then that will also be no, the maximum kinetic energy as well. No? Now, as we move up also, no, so the highest height, no, will also give us the maximum potential energy at the top. Here are related problems now on our potential energy. No? So you may go to this one. No? So these are, again, slides that are found in your Canvas. No? So there are equations that we have here, no, in finding the value of our object. So we can actually in this illustration here, I think what we have here is a stone, no, that is placed, no, at a certain height, no, and we want to know its final velocity at the bottom, no. If maybe now we can determine its final velocity at the bottom, no, given its height, no. Now, if we are to use our kinematics there, no, we can actually solve it by kinematics. But what if we will use our equation on energy, no? So if you have, for example, a stone, no? So let's say this is our object, a stone, no? And it is located at a particular height, no? And it will go down. No? Now, what we want to find is the final velocity of the object at the bottom. We want to know how much is this velocity. But we will not use, no? So let's say the height there is provided. And the height is, let's say, 20 meters. No? Now, if we are to use, guys, our equation on kinematics, we can find the value of the final velocity at the bottom. No? So we can actually determine the final velocity here if we will use our initial and final energy. No? So atong conversion of energy. No? We can use another technique there, no, in finding the value here. No? Now, but let's clear this portion here. No? Allow me to clear this area. No? Let's say we will cover this. No? And let's analyze it using our equation there. So let's see now. So again, if we will relate the expression here by relating it to the total energy at the top and the total energy at the bottom. So the PE maximum at the top added together with the KE minimum at the top will just be equivalent to the one below. Now, however, the minimum values actually could could be considered simply to be equivalent to zero. No? So if this object here, no, if let's say the object there is actually no, do not have a velocity, no, so this one will simply be equal to zero. No? If this one has no height, no, then this value will also be equivalent to zero as well. No? So if the total there happens to be a constant, no, then actually no, PE max, no, or PE2, no, for that matter, we have PE max, no, at the top will just be equals to KE max at the bottom. No? And if they are equal, and if PE max is actually mg times h, no, while KE max is 1/2 mv square, no, or vf square. And therefore, now, if we will solve for the value of vf square or v, no, we can then now simply cross multiply our 1/2 here now to the other side. No? So you will eventually have here 2 mgh, no? And that will be equals to our value mv square. No? We will simply transfer 2 or 1/2, no, to the other side so that we will have no denominator. Now we will notice also that if m now is found on both sides of our equation, that m here now can be cancelled out. No? Again, now we are talking about a certain object, maybe a stone or any object that falls down. No? And again, the location where it is placed is 20 meters, no? And that's how far it will fall down. No? Now, we will realize that the mass of the object at the top will be the same mass that it will strike at the bottom. No? So the mass here is not actually changing. No? So therefore, if it is found on both sides of the equation, if you divide both sides by m, then mass will simply cancel out. No? And then it will just simply leave us now with an expression v square on the right side is equals to 2gh on the left. No? But since this is an equation, we can actually say that v square, no, we will change the location, no, will be equal to twice of g times h. No? Now, if we will solve for v, then we are going to find, no, the square root on the other side. No? So twice gh, and then writing it, no, inside a square root value, no, and allow us to determine actually, no, our final velocity at the bottom. No? So the final velocity at the bottom, no, using our energy conservation equation, no, pwede give, no? So, but of course, no, we will have here PE2 plus KE2 equals PE1, no, plus KE1. No? Again, talking about PE1 to be the minimum and KE1 to be the KE maximum at the bottom. No? PE2 to be the maximum potential energy at the top, no? And then plus KE2 at the top, which is already zero. No? So, no? The total energy at any level, no, can be added up, and we can simply equate that. No? Again, now this is a very simplistic, however, no, way of understanding, no, our, no, energy conservation. No? Any question? So, okay, so this is now an approach that is very much the same. No? This slide here, no, illustrates, no, that object that is about to strike the ground. No? So conservation of it. Now let's go to power. Power is how fast, no, we can finish doing our work. No? So there are machines, aircon, for example. No? One aircon has a higher power than another aircon. No? Now we can see the rated power of a machine, no, labeled in horsepower. No? So horsepower is an expression of that mechanical power, no, that one device can accomplish. No? So one water pump, for example, can do 2 horsepower, no, of how fast it can do. No? Others can do it no in less value, no? Another way of looking at power, no, is when you buy a water pump, no? So if you buy a water pump that has a higher horsepower than a water pump with lesser horsepower, it can fill the tank, no? Both of them can actually fill the tank, no? But which one can fill the tank in less amount of time, no? So maybe, you know, the one with a greater horsepower can finish the job in less number of minutes, no? Or that is if it is in minutes, no? Or less number of hours, no? So again, the horsepower tells us, no, how fast or the rate of accomplishing the work, no? Um, there are cars that can run, no, with several hundreds or thousands of horsepower, no, in just a matter of a few minutes, no, or a few seconds, no. What is power, no, in terms of our work that we've learned already? So if you divide the amount of work that a machine do, no, divide by the time, no. So since that is a rate of doing work, no, so work divided by time is actually equals to this power, no, which we will label, or we will use a unit, no, that is commonly used, which is watts, no? Another one that I mentioned already is the unit of power, which is in horsepower, no? So if you divide the number of joules of work, no, by the number of time in seconds, joules per second gives us a unit called watts. So that's our unit, no, for using, no, Newton, no? So if it's in MKS, no, so the unit of our power there is in watts, no, MKS, kilogram meter per second, no, or Newton or joule, no, per second gives us this value, no? So James Prescott joule, no, is the one that gives us our unit of joule, no? That's James Prescott joule, no? James Watt also, no, is the one that is also the proponent, or was attributed, no, the unit for power, no? Now in the delivery of huge power, no, like the one generated by machines, no, that provides us with electrical energy, the unit of our power there is in megawatts already, no? So several millions of watts na siya da, no? So that's labeled in megawatts, or right now in what, no, gigawatts, no, value, no? Now in the English system, we have the foot-pound, no, per second. And sometimes, no, they equate it, no, with the unit HP, no? So horsepower, no? Now what's the equivalent of this horsepower, no? A horsepower is actually 746 point something, no? Or 745 point something of a watts, no? But when we round it off, no, we can just equate, no, horsepower to an equivalent number of watts, which is equals to 746 watts, no? And that's the conclusion of our lecture, no? And here are some things, no, which you can also, no, apply, no? Maybe we can do this, no, in our, no, future discussions, no?